Okay, so good afternoon to all, and welcome to lecture number 14. And today we'll start chapter number 3. The title of that chapter is Mid-Level Computer Vision, and particularly in that we are going to study feature representation and description. Okay, so in this chapter, as I told you in very first lecture, we'll be taking or we'll be studying, like for example, how to extract the textural features or color features, then shape feature representation. In that, we'll be focusing more on shape features. Okay, so maybe 1 or 2 lectures will finish this color and texture features. Then after that, we'll give more importance to the shape features. So in that, we'll see how to do the region identification. Then what are the different features based on counter-based shape representation and description, and then region-based shape representation like area and so on, and finally shape classes. So these are the contents of this chapter number 3. So in the beginning we will start how to extract the features, texture features, and then color features, and then after that we'll start this shape features. But you know that why features are important, why we are extracting the features from the object or images and so on. The main reason is that I told you in the class, right, like for example, in the class I told you why features are important, because if you compare the image pixel by pixel, then one thing is that number of computations are required are very high. That is, every pixel you have to take the difference of every pixel. So computational complexity will increase. Second reason is that, so for example, one image is of size 512 by 512. Okay, and another image which looks like same, which is the scaled version of that one, and what is 128 by 128. Now we cannot compare this pixel by pixel 128 by 128 image with 512 by 512 image. We cannot take the difference of that one. Another thing is that if the image is rotated, like for example, size is same, but if it is rotated, then this taking simple difference will not work. Or if that image is shifted by 1 pixel, whether it is to the left or right or top or bottom, then also even visual, okay, human vision system cannot recognize that shift immediately, but computer systems will recognize that shift, and then it will not give you the zero difference, even if the 2 images are same or like that. So what is the next abstraction level in the computer vision? That instead of comparing the images based on pixel level or template based approach, why not to extract the features and compare the images or represent those images with less number of values or numbers and so on. Like for example, 512 by 512 image is there, and then another 512 by 512 image is there. If you are comparing pixel by pixel, then number of subtraction operation will be equal to 512 into 512. That many subtraction you have to do. But if you extract the features from the image, like if you extracted 10 features, so you have got only a vector of 10 features, like as a 10 values or 10 numbers and so on. So comparing those 10 numbers will require less amount of time, and computational complexity will be reduced and so on. And even if it is, okay, if your features are designed such that it is translation, rotation and scale invariant, so even if your image is rotated or shifted, translated or scaled version, your system will recognize it correctly and so on. So next abstraction level is very, very important. That is, feature extraction is very, very important and so on. Now for general in computer vision, which are the most important features? Like most important features are like as a color feature is there in the image or object, like texture features are there, and then shape features are there, or spatial relationship features are there, and so on. So these are the basic features which are very, very important in computer vision, okay, to recognize the object or to interpret the image or to analyze the image and so on. So even you might have seen that this one, see that this is the texture. Why textural features are important? So if you look at this image, this is nothing but here zebra. Okay, so this zebra image is also a textured image. Like for example, this pattern is repeated all over entire image. So this pattern is repeated all over entire image. So texture, if you see the texture in the real world, you'll find that at many places texture component is there. Even some of this, okay, people may have wear the shirt like, okay, textured pattern, like only horizontal lines or vertical lines or diagonal lines, or some pattern is repeated on entire shirt or something like that. Or even if you can see your tabletop, some of the texture, okay, this textural pattern is repeated entire all over entire tabletop and so on. Or you can see that if you look at the cloud, okay, some pattern is repeated on the, okay, in the cloud. Or even if you go, if you take the satellite image of jungle area, all those trees are repeated all over entire jungle. So this tree, okay, these trees are called as texels, and then entire jungle is called as a textured image. Or even so, for example, if you see the image of a brick wall, so this brick is entirely repeated on our entire this wall, and then image which is formed is also a trick, this one, textured image. Or even if you take the photograph of your hair, so these hairs are repeated all over entire your head, so that is also a texture image. Or even if you go to the seashore, you know that small pebbles are there or medium-sized pebbles are there. So if you take the photograph of that seashore, you'll find some patterns are repeated all over. Or even if you take the photograph of water in the sea, you will find that some texture is repeated, some patterns are repeated. So texture is, you'll find textural property in many real world object and so on, or even in synthetic also data, you will find the textural pattern. So texture is very, very important feature in computer vision. So texture present in many real as well as synthetic data, for example, clouds, trees, bricks, hair, and fabrics. And you know that another thing is that you might have seen that this tiger and cheetah. Okay, so color alone cannot distinguish tiger and cheetah, because color of tiger and cheetah is same, but the textural patterns of the tiger and cheetah is different. One is having the stripes and another one is having the dots and so on. So from the textural features, we can easily identify whether that is a cheetah or whether that is a tiger. So this is important in content-based image retrieval also and so on. Now, why textures? Because texture is another feature that helps the image segmentation and classification. Also, texture provides the information about the spatial arrangement. See that this is nothing but the textural pattern. So here basically you have this entire image, okay, block pattern, and then checkerboard pattern or stripe pattern. Like for example, this is white pattern, this is black pattern, whereas a checkerboard, like as okay, your chessboard also it looks like as a black, white, and so on. So this pattern is repeated. Now here it is repeated, here it is repeated, this white is repeated, all like that. And this entire image is nothing but the textural image. This is also a texture image because this black is repeated here, and then after that white, and so on. So this is called as the stripe pattern, this is called as the checkerboard pattern, this is called as the block pattern, and so on. And then individual, this element is called as a texel. This is called as the texel. We'll see what is by texel and so on. And this, so texel is repeated all over entire image, and then the image formed is called as the textured image. So texture provides the information about the spatial arrangement of the colors or intensities in the image, right? So spatial distribution besides colors and intensity level distribution, and also texture descriptors provide a measure of properties such as smoothness, whether it is a smooth texture or coarse texture or regular texture, and so on. So this gives the properties. A texture descriptor provides the measure of properties such as smoothness or coarseness and regularity. Now we'll see what is by smooth texture and what is by coarse texture, and so on. So you can see that these are the textural image, like for example, everybody knows that if you take the blanket image, it will look like this one. Okay, so this is the blanket image. Or even if you take the brick wall image, so this brick wall is just like this one. So this brick is repeated entirely all over the image. So this individual brick is called as the texel, and the entire image which is formed with the texel is called as the textured image. So here also this pattern is repeated here, this part, okay, or this pattern is repeated here, here, and here. And repetition is regular in this one. Okay, so this kind of textures are called as the repetitive textures, right? Actually, there are several definitions available of the texture, but you can see that here this is the water image, and you can see that some pattern is repeated all over entire image, but the repetition is random in nature, right? So here also in this image you will find that repetition is random in nature. That's why it is called the stochastic texture. Whereas here repetition is there in the textural pattern or texel, so that it is called as the repetitive texture or like that. And this kind of texture, you can see that pebbles or seashore and so on, or other synthetic images also. You'll find that some of the texels are of small size, some of the texels are of big size. Like for example, some of the pebbles are of small size, some of the pebbles of medium size, some of the pebbles are of a large size, and so on. So repetition is there, but texel size varies in that. So this contains basically a both property of repetition as well as stochastic. So that's why it is called as the which contains the both property of texture. So we can define technically texture as it is a region, okay, in an image. So texture is a region in an image, has a constant texture if the set of local property statistics or other local properties of picture are constant, slowly varying, or approximately periodic. See that this, okay, this texel is repeated. So you can say that this is the set of local properties which is repeated all over entire image, and the image which is formed is called as the textured image. So I hope that now it is clear what is by texture. So texture is nothing but a repetition of some pattern. Now that repetition may be a regular repetition or maybe repetition, or it may contain both the things or like that. Okay, another texture type is like for example coarse texture or fine texture. Okay, now coarse texture means see, this is the primitive, or this is called as the texel whose size is large size primitives are there. See that, say this primitive, this is a large, like as a tiles kind of thing, so which is large in this one, and then it is repeated all over entire image. So this kind of texture is called as the coarse texture, where primitive size or texel size is large. And another thing is that here the variance is small. So in coarse texture, you can say that technical property is variance is small, whereas in fine texture, you'll find that some, okay, small size primitives are repeated all over entire image. Small size primitives are there, and then because of these small size primitives, the variance is larger in that case. So you'll find that larger variance is there in the fine texture. So this is the difference between the coarse texture and fine texture. First one is that in coarse texture, texel size is large, or this texel is also called as the primitive. And here in fine texture, texel size or primitive size is small. Second difference is that because of large size texture primitive, variance is small, whereas here because of small size primitive or texel, there is variance is large. So this is the difference between the coarse texture and the fine texture. Now we'll see what are the ways with which we can do the analysis of the texture patterns. So it is usually difficult to describe the irregular spatial arrangement of the textures, and there is some quality of the image that would make an argue that there is a noticeable arrangement in each image. Okay, so noticeable arrangement is there in the each image, and properties as playing an important role in describing texture, like for example properties may be like as a uniformity or density or coarseness or roughness or regularity or linearity or directionality or direction or frequency and phase. So from these textural images we can estimate the statistical properties or structural properties like uniformity or density or coarseness and roughness. So you can see that coarseness is that, for example, here if small variance is there, so we can say that that texture is a coarse texture. If variance is large, we can say that it is a fine texture, and so on. Then roughness is there. Regularity is that if the pattern is repeated on entire image, then it is called as a regularity. And also linearity is there. Directionality is in, okay, if pattern is repeated in certain direction, then it will have the good directionality property and direction also. And also we can from that we can, if you take the spatial or spectral approach for doing the analysis, we can estimate the frequency, spatial frequency from that one, and also phase angle of that. So from this textual image we can estimate different kind of features and which can be used for recognition purpose and identification purpose. So there are mainly three types which are generally used, widely used for doing this texture analysis. Okay, so which are those three approaches? One is structural approach for doing the texture analysis. Another one is statistical approach. We can find the features by using statistical approach. We can find the features by using structural approach. And third one is spectral approach. Okay, so in spectral approach, you are transforming that texture by taking the transform. Like for example, you are representing that texture in frequency domain by taking the transform like as a Fourier transform or wavelet transform and so on. And then from the transformed image, you can extract the features. Whereas in structural approach, okay, you see that in structural approach, this texel is repeated all over entire image. So you are estimating the property of texture, this texel or primitives, and then you are finding the relationship between all those primitives, and then you are generating that image, or you are reconstructing that image based on the relationship as well as primitives and so on. So a set of primitives texel in some regular or repeated relationship that gives the structural approach. In structural approach, basically what we do, we try to estimate the texel or primitives, and then from that, what are the relationship among all those texels. So we can estimate the basically structure of that texture by using structural approach. Whereas in statistical approach, we will get the numerical values or numerical features from the statistical approach of this texture image. So a quantitative measure of the arrangement of intensity, like for example, what is the variance, what is the energy of that texture, and what is the standard deviation of that texture, and say on, or with, okay, what is the smoothness of that texture, what is the coarseness of that texture, or whether that texture is grainy texture, and so on. So like that way, we can extract the numerical features from the texture by using statistical approach. And more general, it is easier to compute and popular in practice. Many times it is used to find the basically textural properties by using statistical approach. Whereas in spectral approach, as I told you that the original texture image, okay, you are transforming that one into the frequency domain, because your original texture image is spatial domain, and then by taking the transform of that texture image, like for example Fourier transform or wavelet transform or any other transform, you are mapping that one into the frequency domain, and then that from frequency domain you can extract the frequency domain features and so on. So this is based on properties of the Fourier spectrum by identifying the high energy, narrow peaks in the spectrum, and so on. And this is primarily to detect the global periodicity. So basically, overall, for global approach, okay, for considering the image entirely, in the spectral approach, you are considering the image entirely, whereas in statistical approach, you can consider the image locally. So this will be good for extracting the local features, whereas it will be good for extracting the global feature of the image, and so on. Or see that here, I have given in detail, like there are three approaches for texture analysis. One is structural approach. This is based on the geometry of that texture and relationship among all those texels. Whereas in statistical approach, you can use statistical features like as finding the co-occurrence matrix of that one, or histogram features, or local binary patterns, and then random fields. So these are the approaches which are used in statistical approach. Whereas in spectral, what you are doing? You are taking the transform of the texture image. So maybe Gabor transform you can take the Fourier transform, or Laplacian of Gaussian pyramid, or you can take the wavelet transform of the image. So you are representing, you are considering the whole image here, and then finding the either Gabor transform or Fourier transform or Laplacian Gaussian transform or wavelet. Whereas here, to find out this one, you are considering the small portion of the image at a time. So this will basically exploit the local correlation of the image pixel. The statistical approach is good for exploiting the local correlation of the image pixel, whereas here you are considering the entire image at a time, and then you are taking the transform of that entire image. So this will capture the global information about the energy on a different scales. Like for example, you can represent the image in a multiple scale by using either Gabor wavelet, or using wavelet transform, or Laplacian of Gaussian, and so on. And then from those images or subbands, you can extract the features like as a energy feature, or standard deviation, or any other feature, whatever you decide, which will be useful for this one. So this captures global information, whereas this captures the local information. The statistical approach is good for characterizing the texture image locally, whereas spectral approach is good for characterizing the texture image globally, and so on. So where the statistical approach will be successful? This is successfully analyze the texture with weak edges or random natures. Okay, so this will give you more accurate result where the textures with weak edges are there or random in nature is there. Then statistical approach will give you the better result. Whereas in the spectral approach, where we can use a spectral approach, this is best suited for the texture which is periodic or almost periodic texture. So there you find that spectral approach will give the best result among all this one. So these are the basically techniques for doing the texture analysis. First one is structural, then statistical, and spectral. So we'll see one by one. So structural texture description, as I told you that you are finding the primitive first, right? So estimating that primitive, and then a relation between that primitive, neighboring primitive, and so on, and then you can reconstruct that one. So a simple texture primitive can be used to form more. So for that, finding the primitive, what you can do, you can use the geometrical properties like as a circular, rectangular, or a square, or triangular kind of this one. So you have to identify basically that this one primitive, and then you have to establish the relation between among all those primitives. A simple texture primitive can be used to form more complex texture patterns by means of a sum rule that limits the number of possible arrangement of the primitives. So descriptors like, for example, a description of the texel is nothing but the primitive, and a specification of the spatial relationship means basically you are finding the spatial relationship among this one, and this is suitable for man-made or regular patterns. So structural approach is suitable for man-made texture or texture having regular patterns. So it is good for that. Okay, so what are the steps for doing the finding the structural texture features? So these are geometry-based description, and the characterization of spatial relationship is obtained from Voronoi tessellation of the texels. So what are the steps basically? The first step is that you have to segment the image to extract the texel. Means from entire texture image you have to find out the texture. Okay, segment that texture texel. Okay, and this, you know that this texel is entirely repeated or entire image. Like for example here, this one, you have to segment this texel, and then you know that this texel is repeated all over entire image. So, and then after that you can find out the relation between this one. So once you know that this is, suppose for example, the rectangular kind of texel is there, so this rectangular kind of texel is repeated all over entire image. So first thing is that in a structural approach you have to identify which kind of texel is there, so you have to extract that one. So segment the image to extract the texel. Then after that construct the Voronoi tessellation and calculate the shape features of the polygons to group the polygons into a cluster that defines uniformly textured region. So basically you have to first segment the texel, then construct the Voronoi tessellation, and then calculate the shape features of the polygons to group the polygons into a cluster that defines the uniformity into the texture region. For example, here see that this is the one texel like that. So this basically texel is what kind of shape is this one? Hexagon, no? Hexagonal shape is there, and within that one there is a circular. So there are basically two texels. One is circular and another one is hexagonal, and the circular is inside this hexagon, and so on. And then you can say that hexagon is having intensity equal to 255, whereas circular, within that circular intensity of all pixel is this one. So once you segment that one, so this is the entire texel which is repeated all over entire image. So you have, okay, this is one texel which is repeated all over entire image. So first thing is that you have to segment this one. So construction of Voronoi tessellation is that let us S be the set of centroid of texels, and then for any pair of point P and Q in the S, the entire this one, create the perpendicular bisector of the line joining them, and then suppose for example let HQP be the half plane that is closer to P with respect to the perpendicular bisector of P and Q, and then Voronoi polygon of P is defined by VP is equal to the intersection of this HQP for Q belongs to S and Q belongs to P. So basically you have to find out the relation between all those things, and then see that intersection between this one and this one is 0, right? Between texels, all those texels are repeated. There is no basically overlapping of this texel all over entire image. So they are okay. Intersection of that one is 0 in that case, right? Now, second approach for texture description is statistical approach. So what is the motivation for extracting the texture statistical texture features? So first thing is that you have to segmenting out the texel is often difficult in real image. So you find out this one. So this is very basically easy because your texel is having the hexagonal property as well as circular property. But sometimes it may happen that if texel is irregular, and then relation among them is also finding relation among them is also difficult. So in that, okay, in such situation, structural approach will not be useful. What is next approach or another approach? So segmenting out the texel is often difficult in real images. So numeric quantities or statistic of the texture from the color or intensity themselves can be computed or estimated. Like for example, what is the energy value of that texture? What is the variance of the texture or standard deviation of the textural intensities and so on. So that will represent basically a numerical feature of the texture. So what is the advantage of this one? Advantage of statistical approach is that it is computationally efficient, and this works well both for segmentation as well as classification in the texture image. Now, what are the ways, different ways with which we can estimate the textural properties? So first simple method is the age, density, and direction. See that how we can calculate this one, age, density, and direction. Like you can extract the age histogram also or local binary pattern. Okay, finding the local binary pattern of the texture is another approach for statistical. Then histogram. Okay, plotting the histogram of the texture image and finding the features of that one. Then co-occurrence matrices and features can be calculated by using statistical approach. And then also autocorrelation and power spectrum of that textural. So these are the different methods for finding the statistical features of the texture. Like for example, age histogram. What do you do in that age histogram? Like for example, you can basically divide the whole image into the entire total directions are like as a 360-degree directions, and then from this you can divide the 360 direction in like for example in total 10 this one or 12 different beans. So in one bean, what will be the direction? 0 to 30, then 30 to 60 will be another bean, and so on. So that way you'll get just 12 bean, and whatever the basically textural properties are there, that will be represented in one bean, and then you can plot the histogram of that entire textural image and so on. Okay, so see that age density and direction. That age detection is simple and easy to apply. You have already studied in our second chapter how to detect the ages and so on. And the number of age pixel in a given fixed size region gives some identification of the busyness of that region. See, that means what they are doing here in age density and direction. They are basically estimating the ages, means finding the ages by using simple age detection technique, and then the number of age pixels they are calculating in a given fixed size region. That gives some indication of the busyness of that region, and the direction of the edges also describe the characteristic of the texture vector. Means you know that edge magnitude is there and edge direction is there, so from that also you can estimate the textural property in statistical way. Then the edge density and direction, the output of each point from edge detector, that is the gradient magnitude and then the gradient direction. So you are finding the direct magnitude and direction, and then edgeness per unit area, you are finding the edgeness per unit area which is given by the magnitude of this gradient, and then if it is greater than certain threshold value divided by total number of pixels n. Okay, so that will give you the edgeness of this one. So edgeness per unit area measures the busyness, means if that pixels are more on the edge, then it will be more busy, and if it is less, then it will be less busy or something like that. So, but not the orientation of the texture here. Okay, so it will give you the direction. Then edge density and direction. So extended to include both busyness and orientation. Here, let H magnitude, okay, denotes the normalized histogram of gradient magnitude of the region R, and H direction. So that is nothing but the direction denotes the normalized histogram gradient orientation of the region, right? So you are finding the magnitude of the region and direction of the region, and the quantitative texture description of the region R is given by what? The H magnitude and H direction. So you can get the two values here, or you can find out the L1 distance for the comparison. Like for example, if you have the two regions and you would like to see that whether these two regions are similar or not, H1 is one region, H2 is another region. So you can just take the difference between the H1, all the features of H1 with all the features of H2. So 1-to-1 difference. So if they are same, definitely it will be 0 value. If they are different, it will be having non-zero value. So from that also you can classify the textural object or segment the textural object and so on. So like that way, from edge density and direction, you can simply calculate the magnitude of that region and direction of that region, and then so that is nothing but your numerical values. So this is, suppose for example, H1 is one area, okay, having this magnitude and direction. H2 is also another area which is having magnitude and direction. So you can calculate whether this difference between the similarity between H1 and H2 by just taking the difference of those features, magnitude and direction features of H1 and H2. So like that way you can do it. Now, another way for extracting the textural feature is this is very important, widely used in many research areas and so on, local binary pattern. So I think in our next lecture, we'll continue with from local binary pattern, how to estimate the local binary pattern of the texture, and then the spectral approach and also color features. So in our next lecture, we'll do this one. So we'll stop here. Thank you very much.